Hi, everybody. In this meeting, we're going to be going over the contest prompts from the Clements High School contest, and then we'll be going over the binary search algorithm, which is really useful. So assuming you've read the first problem by now, we have as input, we're given a bunch of food items or just a bunch of strings, a bunch of words, and you have to output the number of words that Dwight writes down. So over here, you can see he writes down cabbage, potato, potato, beet. And there are three different words he writes down, cabbage, potato, and beet. So that's why the answer is three. You only want to output how many unique words that Dwight writes down. So are there any ideas for how to solve this problem?
Use a set.
Yeah, that's correct. So this is a very easy problem if you attended our ArrayList maps and sets lesson. Basically, a set only stores unique values. So all you would have to do for this problem is read in a string, add it to a set, which only stores unique values, and then just print out the size of the set. That's the solution for the first problem. The second problem was just pretty much finding the distance between two coordinate points and finding out if one was smaller than the other, then printing out keep going or not quite. If you competed in the contest and you want me to go over some specific problems, just let me know and I can also show my code. But these beginning problems are really simple and I want to get to binary search eventually. So this next problem is called Ace in the Hole. In this problem, you were given a bunch of scores that this person's made in golf, and you had to output the sum of the three highest scores. So over here, his scores were 6, 3, 1, 4, 6, 5, 2, 5. The three highest scores were 6, 6, 5, which has a sum of 17. Does anybody have any ideas for how to solve this problem? You want the sum of the three highest scores.
You could just do array sort and
How
then
about
take the
Aryan Bhai? I came to our
highest.
girl.
I think somebody is not on mute. But yes, what Madhu was saying is correct. So you just read this into an array, you sort the array, and what happens when you sort it is the numbers at the end are the largest. So once you sort it, all you have to do is just add up the last element, the second to last element, and the third to last element. That's your answer. So you can see these problems are pretty basic initially. And then the last couple of problems in the packet are actually really hard. So in this problem, we have a bunch of fence posts, and we can cut wood from the fence posts, and our goal is to make them all be the same height. So over here we have fence posts of length 2, 4, 3, and 1. We want them to be the same height, but we can only cut wood out. That's why our fence posts would have to be of height 1, 1, 1, 1, because the smallest number is 1, and you have to cut one from the two to get to one. You'd have to cut three from the four to get to one. You have to cut two from the three to get to one. And that's a total of six units of wood that you just cut to make all of these the same, to make all of them one. And you cannot add wood. That's why you have to cut wood and do subtraction. So for this problem, the way you do it is you just go through, find the smallest number, and that's going to be the height of all the fence posts. And then what you have to do is just add up the differences between two. You have just add 2 minus 1 plus 4 minus 1 plus 3 minus 1 and so on. That is that problem. In this problem, these are the scores of this person called David. You have to output every time he gets a new high score. So initially he has a score of 0, then he starts playing the video game. He gets a score of 10. 10 is his new high score. We print out 10. He gets 5. 5 is not a high score. Neither is 10. He gets 200. 200 is his new high score. We print out 200. He gets 50. That's not a high score. He gets 300. That's a new high score. And you print that out. So the solution for this problem would be to have a variable that's the maximum score that just keeps track of his high score. So initially his high score should be set to 0. Then you go through these numbers, and every time you come across a number bigger than the high score, you print it out, update your high score, and continue. Yeah, so these are the problems. Is there anybody who competed in the contest who wants me to go over specific problems? I think there are only three people in here or two people in here besides the officers who actually competed. Yeah, there are only two people besides the officers who competed, which is disappointing. We'd like to see more people compete in these competitions. Yeah, so these next couple of problems get harder. And you guys can try to attempt them on your own. And if you have any questions, you can ask. Yeah.
Sean, Raid has a question.
Oh, sorry, I didn't see the chat. I have to pull it up. Yeah, can we go over question 12? Okay, so was your question 12 the organization? I'm not sure if we had the same problems or not.
We had different questions.
Oh, we did? Okay. If you could give me the link to it, I could take a look right now.
Sure, let me get it.
Yeah, so I'll just continue with number 6 in the meanwhile. So in this problem, you have Grace who gets these scores, and then you have to, um, she's given an array of values, and you take the lengths of consecutive values you take the length of consecutive subarrays that have the same values, you square those and you add those together, and you want to try to arrange these numbers so that you get the maximum possible sum. So for example, we have 1 5 by itself, that's 1. Here, let me open up sketchbook. So in this example, we have 5, which is by itself, so that's 1 squared. We have 4 by itself, which is 1 squared. We have 6 by itself, which is 1 squared. We have 4 by itself, which is 1 squared. And then we have two 5s next to each other, so that's going to be 2 squared. In this example over here, 5, 5, 6, 4, 4, we have 3 5s next to each other, so that's 3 squared. We have 1 6 by itself, so that's going to be 1 squared. And we have two 4s next to each other, so that's going to be 2 squared. And the goal is to arrange these numbers in such a way that this sum over here is the maximum possible. So you can see over here, in the way they give us the input, the sum is pretty small. It looks like it's just 8. But in the actual answer, if you order it like this, 5, 5, 6, 4, 4, the optimal answer is going to be 14. So that's so you can see, if you look at some of the test cases, you'll realize that the optimal solution is to put the numbers that are the same next to each other. Because let's say we had two 5s and we had one 1. So we have something like 5, 5. We had a 1, we have a 1, and then we have a 5 and a 5. Right now, our answer is going to be 2 squared because we have two 5s next to each other. We also have 1 1 by itself, so that's going to be plus 1 squared. And then we have two 5s next to each other, so that's going to be 2 squared. So the value we're getting from the 5s is 2 squared and 2 squared, which in total is 8. But if we had put the 5s next to each other, so imagine they had been 4 5s next to each other, the value of this is going to be 4 squared. And 4 squared is 16. 16 is greater than 8. So having it be 1 5 5 5 5 gives us a higher value than 5 5 1 5 5. And the reason for this is because if we have two numbers, let's say we have two numbers, a plus b squared is greater than a squared plus b squared. And that's the proof or reasoning behind why that works. So for this problem, you would sort these numbers and then you would just keep track of how long that subarray is. And now I'll switch over to problem 12 from this contest, the suspicious imposter. I'll need some time to read it. Madhu or Kanish, do you guys want to go over some of the other problems or other things if you have anything while I read it?
We didn't do this contest. So.
Yeah, we didn't do it.
Okay, that's fine. As an imposter, you want to bonk to other crewmates without drawing suspicion. Unfortunately, all 8 crewmates are suspicious of you to some degree. Each crewmate is assigned an ID number and a suspicion level. The IDs of the crewmates range from 1 to N.
Don't you wish you could find people's suspicion level in real life?
Yeah. Okay, yeah. So this is that's a really good question, right? I'm glad you brought it up because this is actually a custom sorting question.
Yeah, we
Yeah,
went over
Madhu
this
and
last
Kanish.
week.
Yeah, Madhu and Kanish went over this last week, so this is great. So basically, in this problem, you have a bunch of people that you want to bonk, and these people have an ID number and a suspicion level. And you want to bonk them in a particular order. You want to bonk the people with the lowest suspicion first, and then bonk them in increasing suspicion level. If there are two people who are tied with the same suspicion level, you want to bonk the person with the lowest ID number. So you want to bonk. So that's what the problem is, and the input is the ID of a crewmate. So one, the suspicion level, and the ID of the crewmate's buddy. What? Oh, I didn't read this part over here. Oh, okay. Oh yeah, I didn't read that. Every crewmate has a buddy whose suspicion level will increase by 1 if that crewmate is found bonked. What is the input size? Oh, okay. So the input size on this problem is pretty small, actually. For this problem, you would be able to try. For this problem, you'd be able to do like an n cubed solution. Even an n to the fourth solution would work. But basically, for this is what you could do is you could have a hash set that keeps track of all the. You could keep track of a hash. You don't even need a hash set. You could just have a Boolean array that keeps track of whether someone is bonked or not. So I'll switch over here. We can have a Boolean array, so something like Boolean bonked. And just for this first test case, we have 3 people, so I'll just say equals new Boolean 3. And then what you're going to do is for int I equals 0, for int, we could say for int crewmate equals 0, crewmate is less than 3 crewmate plus plus. So this is to make sure that we bonk every single crewmate. We're going to go through 3i plus plus, and then we're going to check if this person is bonked. Continue. We also want to keep track of the person that we want to bonk. So int position. In position, I'll just set that to -1 for now. I also want to keep track of the suspicion level because I want to find the person with the lowest suspicion level. So that's why initially I'll set that to 100. And I want to keep track of that person, the person's ID. So I'll also set that equal to, I think we wanted the person with the lowest ID number. So I'll also set that really high. And the idea is if the suspicion level, let's just pretend like I have an array called suspicion that keeps track of the people's suspicion level. So I'll just check if suspicion level of, if suspicion, okay, I'm not going to code the whole thing, but the idea is you just go through the array and then you check if that person is not bonked, do they have a lower suspicion level than the person I'm currently looking at? If they have a lower suspicion level, you want to take that, you want to bonk that person. So then you'd set your suspicion level to that person's suspicion level. You'd also update your position. And then you keep on doing this. You go through every single crewmate to find the lowest unbonked person. Once you find that lowest unbonked person, you're going to bonk them by setting bonked of that position. That's why we have this position variable. That's the person we're going to bonk. You set bonked of position to true, and then you print out that position number. And I can code this later towards the end. I didn't code this properly. I hard coded the 3, and I still have to read in the input and stuff. But if you want to see the solution for that, we can go over that in the end. And now we're going to transition over into binary search. So this would be a good time to pull up, IntelliJ, Eclipse, whatever software you use to code. And it's fine if you have to use REPL.it for now. And once again, I couldn't find my drawing pad, so I'm going to have to draw with my trackpad. But if you remember about 2 weeks ago, there's a binary search problem on UTD's contest, and it was a guessing game problem. You had to they gave you a number from between 1 to 100, and you had to guess what number that is in less than 10 tries. And I talked about how if we had to guess a number between 1 to 100 trillion, and we tried guessing every single number, that would require 100 trillion guesses. But if we used a binary search, it would require between 1 to 40, or sorry, it would require between 40 to 50 guesses. And just to recap what a binary search is, or yeah, to recap what it is you have the search space where your answer possibly lies. So the answer to our problem, in the case of a guessing game, it's the person's number that they're thinking of. So the answer to the problem lies somewhere within this range of 1 to 100. And we don't know what it is, but we know that it has to be somewhere within this range. So instead of guessing two and then that person saying two is not my number, and then you guess three and four and five and all the way up to 100, which is really slow, the idea is you guess in the middle. So you guess smack in the middle at 50. Well, it's not exactly in the middle, but that's fine. So you guess 50, and the reason you do this is because there's a 50% chance their number is actually bigger than 50. There's a 50% chance that their number is smaller than 50. But now what you've done by guessing the number 50 is you've narrowed the search space down by 50%. So let's say they say, no, 50 is not correct. My number is actually bigger than 50. Now we know we don't even care. We don't care about this at all. We don't care about the range of 1 to 50 because they just told us their number is from 50 to 100. This space over here is not important. So now we're going to search from 50 to 100. And then we keep on repeating. We guess 75. Maybe they say 75 is too high. We don't care about this part over here. Then let's say we guess 62. They say 62 is too low. So we don't care about this space over here. And then we keep on guessing in the middle until we come across their number. And that's how a binary search works. And runtime for this, if you remember back to our time complexity lecture a long time ago, is going to be log base 2 of n, which is really good compared to n. So the graphs of that would be like, this is n, it's linear, and it gets really, really big. And then for log base 2 of n, it's like this. It's much, much smaller, especially for really large values of n, which is why binary search is really important. So are there any questions about what I just covered? Now, how would we actually code this? It's not too difficult to code, and it's actually fairly short. So the way that you would do this is you'd have a low variable and a high variable. And these keep track of your range. So low is going to be set to 1 in this example because we're guessing numbers from 1 to 100, and high would be 100. The numbers that you're going to test are going to be the number in the middle, right? Like in the example, the prior example, we just saw that we would guess 50 first because 50 is in the middle of this range. So what we're going to do is we're going to guess a number that is equal to low plus high divided by 2. And let's just call this mid. Okay, so we're going to guess this middle number, which is the average of low and high. And then what we do is we check if this middle number is lower than the actual guess. So let's just say if mid is lower than the actual guess. So I'll just say guess. Then we're going to have to do something. In this example over here, let's say we guessed 50, and let's say the guess was 70. The actual number was 78. This shouldn't be guess. This should be number. This should be answer. Mid is our guess. I misnamed it.
If you already know what the answer is, why are you searching in the first place?
Yeah, that's a good question. I'm just doing an example over here. So binary search problems and contests are not going to be guess this number. It was just that case for UTD because they were trying to introduce competitors to interactive problems because they're going to be using that in their next contest. Typically, binary search problems are coupled with something else. UTD actually had two binary search problems. One of them was the guessing the number problem, and the second one was Dijkstra's along with binary search. So that was a little more complex. So I'm just giving a basic example so you get an idea of how it works. So let's say our answer is 78 and the middle number that we're guessing is 50. In this case, what range are we interested in looking at? If we, like, let's say we guess 50 and the person says, no, my number is actually bigger than 50. Does that mean their answer is over here on the left or on the right? And you can type right or left into the chat. Yeah. If they tell us, no, my number is bigger than 50, then we know it has to be somewhere over here. What did I say low and high were representing again? They were representing the ranges that we're interested in looking in. So the low is initially set to 1 and high is set to 100 because those are the possible ranges for our answer. But now the person just told us, no, my answer is actually higher than 50. So what we're going to do is take this lower bound over here, this low, and we're going to set it over to 50. So basically, if the middle number is less than the actual answer, we are going to, if the middle number is less than the actual answer, that means our guess was too small. So now we're going to set low equal to the middle number plus 1. So now our new range of numbers will be from 51, whoops, it will be from 51, well, it looks like it changed the color, but that's fine. It'll be from 51 to 100. And now what's in the middle of 51 to 100? And you can just give me an integer. You don't need to give me an exact number. 75. So 75 is in the middle. So now let's say our program guesses 75. And let's say, well, actually for the purpose of this demonstration, I'm going to change the 78 over to a 60. So let's say the actual number the person was guessing was a 60. So in the case that the middle number, which now is 75, 75 is our new middle number. In the case that 75 is greater than the answer, so 75 is greater than 60, are we interested in looking at this upper space over here anymore? We know that 60 is smaller than 75. They just told us your guess is too big. Because our guess is too big now, we're going to take this upper bound and we're going to move it over here. So this is going to be high. Because we don't care about, we don't want to look at this space anymore because the answer is actually smaller than 75. And like this, we use these two variables, low and high, to keep on narrowing down the space. And we keep on making it smaller and smaller until we find the answer or until the low and high are equal to each other. And that's when we stop. And we implement this by keeping track of these two, by using these two variables to keep track of our upper and lower bounds. So now that we understand what binary search is, we know what it is, and we've taken a look at how it works, we're going to code it together. So you should have REPL.it or some sort of software to program pulled up. And over here, I just have IntelliJ. We're going to make a basic guessing game, and we're going to go through this a little quick. So I have my main method over here. Oh, and let me know in the chat if you need some more time to pull up the software to code. Does anybody need any time? Okay. So you could accept the user input from the scanner using the scanner class, but because we're doing a demonstration, we're just going to hard code the target. Or actually, I'll call this guess. So this is the user's number that they're thinking of. And just like I said just like I showed earlier, we're going to have a low variable that we're going to set that equal to 1, and we're going to have a high variable. We're going to set this to 100. So the user is guessing a number between 1 and 100. And now this is important. This is how our binary search actually works. So we're going to say while low is less than or equal to high. So while our lower bound is less than or equal to our upper bound, we're going to go through, and the middle number, the guess that we're going to make, so this middle number, the 50, the 75, is going to be equal to the average of low and high. So low plus high divided by 2. Is this making sense to everybody so far? This is the middle number that we're going to guess. Low and high are the upper bounds, 1 and 100. Mid is the number that we're going to guess. And then what we say here is if mid is equal to the guess. Wait, why did I call this? I'll call this answer. Technically, mid is the guess our program is making. So if this number in the middle that we're looking at is equal to the answer, we can print out found plus mid. So you can just say we found the number. And this is important. Now that we found the number, we want to break out of the loop. So we break out. The second case that we're going to check for is if mid is less than answer. So this is pretty messy. I'm going to delete it and redraw it. So in our code, mid is equal to the average of low and high. So mid is going to be 50. Let's say the answer is actually 80 over here. So the case we're checking for is if 50 is less than the answer, which is 80. If mid is less than the answer, what did we say we want to do to our lower and upper bound variables? Which one do we want to change? If our answer is actually in this range and we don't care about that, which one of our bounds do we need to move and where do we need to move it? Oops. So I see two people saying upper. Yes, that's correct.
You said that the answer is in the upper range?
Yeah.
So then you would need to change the lower bound because it's obviously not in the lower range.
Yeah. So Babia and Matthew got it correct. You want to move the lower bound to 51 now. You don't want to move the upper bound to mid because we don't care. We know that the number is in the upper range, but low and high, the lower and upper bounds tell us where our answer is. Our answer we know is no longer from 1 to 100. We know we can narrow it down to 51 and 100. We know that number is 80. We know that, well, actually, we know the number is bigger than 50. We don't include 50 because if you look over here, technically the middle number is the number we're guessing, right? So we're going to check if the middle number is equal to our answer. We print it out and break. Because in addition to testing whether their actual number is bigger than 50 or less than 50, if their actual number is 50, we don't need to do any more searching. We can just print out, we found your number and get out of the loop. It's only if their guess is higher than the middle or if it's lower than the middle that we want to keep on searching and narrowing down. But if we actually manage to guess it smack on, like let's say they were thinking of a number from 1 to 1000, it was actually 500 and our program guessed 500 on the first try, well then we're done. We don't need to go anymore. So that's why we set it to 51. So that's why over here, if our guess was too small, because our guess was too small, we're going to set low equal to mid plus 1. And the last case, we're going to use an else for that, is if our guess was too big. So if our guess was too big, we don't want to search from 1 to 100. We don't want to search from 51 to 100. We want to search from 1 to 49 because our guess was too big. We're going to bring the higher bound down lower. So we just say high equals mid minus 1. And this is actually all a binary search is. So now if I run this, and your code should look like mine. Once we run this, it will print out found 78, which is nice. And just to demonstrate how this is working, I'm going to go ahead and print out the middle value each time. So I'll print this out so you can get a better idea of how the binary search algorithm works. So you can see the first guess it makes is 50. Then it makes a guess of 75. It realizes 75 is too low, so it increases the lower bound to 76. It then searches from 76 to 100 and guesses 88. 88 is too high, so it goes lower. It makes high lower. It guesses 81. It finally guesses 78 and says found 78. Are there any questions about this? Yeah, so now we're going to do a binary search example with an array. And what we'll do is we'll write a program that tells us whether an array contains a number or not. And it'll also tell us where that number is. Because let's say I had an array of numbers, like one. I'm just typing out some random numbers here.
Loop stop. I must have.
Sorry,
Like, what did you do to stop that loop before?
can you say that a little
Oh,
louder?
I missed the break statement. Okay.
Yeah, the
Okay.
break statement's over here. So we're going to print out found and then the number because it's equal to our answer, and then we break out of the for loop. And if the number was not found, so let's say I made this like 1,000.
I missed the break statement. I wouldn't stop. All good.
Okay. So over here, I have this array with a bunch of random numbers. I'm just going to delete duplicates. And let's sort this array. So arrays.sort. So now we have this sorted array. And one important thing to note is whenever you're doing a binary search with an array, the array has to be sorted, because the way that the binary search works is it says, if my guess is too low, all the numbers on the right are bigger than me. And if my guess is too high, all the numbers on the left are smaller than me. And it uses that to its advantage to then cut the space in half each time. But if the numbers are random like this, like 38 is over here, it's not going to work. So this is really important. You want to always sort the array before you do a binary search. And what we're going to do in this example is we're going to have a target number that we want to find the position of. So for example, let's say we want to know where the 19 is in the sorted array. So we'll have a target number that we want to find called that's set to 19. And then for our, we're just going to print out we found the target at position and then target and array. So this is a function we're going to write. It's going to be called find, and it's going to accept an integer that we want to find and the array that we're actually looking through. So let's go ahead and write this method because it does not exist. And it's going to be public static int find int target int array. And over here, we're going to have our low variable. What should the lower variable be set to when we're searching through an array? And I'll give you a hint. The lower and the upper and lower bounds refer to the size of the array, how many elements we have in it, and the indices. So the lower and
0.
upper bound, yes, it should be 0. And what should the higher bound be equal to? What's the last index in the array?
Length minus 1.
Yeah, so array.length minus 1. And then what we're going to do is we're going to have, just like we did earlier, it's going to be almost exactly the same. We're going to have while low is less than or equal to high, int mid equals int mid equals the average of the two of them. So we're going to average it. And then we're going to say int num equals array of mid. So let's say we had a smaller array of numbers like 1, 2, 3, 4, 5. Mid is going to be equal to the middle position. So mid would be equal to 2 because 2 is the middle position. And num is the number actually at the middle position. So the number at position 2 is a 3. And that's what num is equal to. So our logic is if this number, just like in the binary search, if our guess was equal to the answer, we print it out and we break. Over here, we're going to check if this number is equal to the target. Well, we just found the number. It does exist in this array. So we're going to return this position. And the position we're at is mid. So I can write this over here. Mid is the position, and num is the actual number in the array at that position. Does everybody understand this? Low and high are the lower bounds and upper bounds for the array indices. That's important to note. Over here, high is not equal to 38. Even though 38 is the biggest number in the array, that's not what high is. High is the last index in our array. So what we're going to do is check if the number that our program just tried, if the middle number is equal to the target. We found the target number, so we're going to return mid, which is its position. Otherwise, if the number is less than the target, so let's say for this example, our program came across 7 and the target is 19. So if our number is smaller than the target, we want to shift our lower bound up, because if we have these numbers, like let's say it's from 1 to 38, our answer, the number we're looking for is a 19, which is over here. Let's say our program guessed 7. 7 is too small. So what we want to do is take this lower number and bring it up over here. So that's why, just like we did before, we say low is equal to mid plus 1. And then in our else statement, we're going to say high equals mid minus 1. And you can see this is red because it's saying that we need to return something. It's missing a return statement because this return statement is inside of an if statement, which means our function may not return something if we don't find it. So if we do not find the value, we're going to return -1, and we can print out over here, did not find target. And then I will run this code. So you can see it said it found 19 at position 6. We can also print out which numbers it's trying. So we can say trying and then that number. So you can see it will say trying 12, 12 is too small, trying 20, 20 is too big, trying 17, 17 is too small, trying 19, and then it finds 19. Let's say we chose a number like 100 or 1,000. 1,000 is not in this array. So when we run this code, it's going to print, see, it prints over here, did not find 1,000, and it returns -1, which is not a valid position in an array. And that's how this binary search for an element works. Are there any questions about this? Binary search is a really powerful tool that's used for a lot of hard problems. Um, one of the problems over here you can check out is from Misako. Where is... I'll add it to the list of problems. Oh yeah, I also added some BFS problems to this list over here. So 3 weeks ago we covered BFS. BFS by itself is an easy to understand example, and once you practice coding it, it'll be simple to implement. And these are some more challenging problems actually using a BFS. So I highly recommend that you check them out. They're actually really fun. The last two over here are really fun problems, fire and coast length. So check that out. And I can add a binary search problem there. Yeah, and that's about it for today's meeting if there are no questions. But before you go, there are some things that I want to put up. We made a feedback form about the meeting format because we want to know how to better structure our meetings and what kind of stuff you want us to do in the meetings. That way everybody can enjoy them. So I'll post the link to the chat or right now. So this is the link. Wait. That's the link to the Google form. So make sure to fill that out before you leave today's meeting. And another thing that we're thinking of doing in Computer Science Club is hosting a winter course for teaching Java to students. So if you have a younger sibling who may be interested, or you know anybody who wants to learn how to code and wants to learn to code in Java specifically, you can let them know that we're doing this. Here is another link that you can share with them, and you can check out yourself, tinyurl.com/winter coding course. And we'll basically be covering the basics of Java. So everything that Madhu and Kanish did in the beginning of the year in the beginner breakout room, we're going to be doing in this coding course, plus extra stuff like object-oriented programming and all sorts of cool things. So if you know anybody who's interested in learning Java, please share that link with them so we can know who's interested. And that's it for today's meeting. Thank you for coming and enjoy your Thanksgiving break. Bye.